So yeah, I just want to say it's a pleasure to be here tonight to talk to you. Thanks all for coming out to see this talk. And I don't know if any of you have been to any of the rest of the series, but I hear it's been a great success, so hopefully I can give you something exciting to think about tonight as well. So the talk I'm going to give you is split into two parts. First of all, we're going to look at polymers in general. We're going to look at their properties and think about why they're such an important material to us. What properties do they have that mean we use them every day and that they've invaded almost every area of our life? And then in the second part, I'm going to move on to talk more about my research, which is in the area of biodegradable polymers. So, there we are. So first of all, what we need to do is define what we mean when we say polymer. And a good definition, the broadest definition, is that it's a large macromolecule, it's a large molecule that's made up of lots of repeat units. And a nice way to demonstrate this is with a paperclip chain. So if we have one paperclip, we can make that, oh, I can't get one off now, we can make that our repeat unit. And then we have, if we join lots of them together, we have a polymer. It's made up of lots of paperclips, but it's a much larger molecule than just the paperclip on its own. And again, we can have just one long chain like that, or we can have something branched, we can have something in a circle. There are lots of different structures for polymers. And the word polymer comes from the Greek polis and meros, meaning many or much, and parts. So it means there's many parts to this polymer. So now we've defined what a polymer is, let's think a bit more about the structure of one, because although we've got this chain, how does it really build up into the materials that we have before us every day? And so, there we are. So looking at this, some polyethylene wrap that you might use on your food, if we kind of zoom right in on that there, then, and I'm sorry this has not showed up very well, but you can see we've got a real network of chains there. If you can see the pale blue, and you can imagine that all of these individual chains are all randomly interlinked, that there's not much order to them. We call it an amorphous material. And if we zoom in even further, say on just on one of the chains, then we see that we've got these individual chains here, which is what we were looking at with the paper clips again, and each one of those is the same. Do we have another point? Ah, there we are. Each one of those is the same. And if we do one more zoom in on one of those molecules, in this case, you can see that we've got two carbon atoms, and they're bonded together. There's a chemical bond between them, and then each one of those then has another chemical bond which goes on to form the chain. So the individual molecules of the chain are bonded together by chemical bonds to form this very strong material. And so you can see that all the way down from the macro scale, we can follow that all the way down to the molecular scale of the polymer. And in the end, that's what chemistry and polymer chemistry is all about. It's about looking at the properties we have right up here that we see and that we use, and then following the chain all the way down to see what exactly happens on the scale of molecules to make these properties up here. And I've just put in this circle here just some of the words that I think people would use to describe plastics, and some of the reasons maybe that we use plastics rather than just relying on metals and wood and other natural materials. And I think flexibility and elasticity is one of the main properties that we like in plastics. We've got a good strength to weight ratio as well, and of course you know that for the same often for the same weight as metal or something, you can have a piece of plastic that's just as strong, that does the job just as well, but is much lighter, and so is very well suited to the application. And something like transparency is another quite good property that we like in polymers. So what is it that makes polymers special? What property is it that makes them flexible, that makes them elastic? To think about this question, we need to think about states of matter a bit. So first of all, let's just think about something like water, which we all know, and we're all familiar with the different states of matter as applied to water. So below zero, water exists as ice, of course. So we've got some ice cubes up here, and you know that if you hit those ice cubes with a hammer, they're very brittle, they'll smash. On a molecular level, the molecules of water are sitting in a very ordered manner, and they all have forces which hold them in place, and they're joined to their nearest neighbours on this side and this side and this side. And so it's a very rigid material when it's a solid. And then if we go through 0 degrees, the water will melt. We'll get to the liquid state. And in that liquid state, you know that water, well, here's some water here. It flows. It will hold it will take the volume that it's set at. It will take the shape of the container it's in. And again, on a molecular level, we've broken some of those forces, the ones that were really rigidly holding the molecules in place. But there are still lots of forces holding the molecules together, but they can move somewhat through the liquid. And then finally, if we take the water above 100 degrees, we get steam, which is the gaseous state of water. And here we've broken all of the intermolecular forces, really, and those molecules are very far apart, and they're moving very fast. They've got a lot of energy. And so then if we move on to think about polymers, why is it, for instance, if I just take this piece of plastic, it's a solid. I think you'd all agree it's a solid, but it bends. And so if we've said that things as a solid are very rigidly held together, how does this bend like this? Now the answer is to do with the fact that we've got long chains of molecules of repeat units. So again, this is hard to see, I'm sorry. The pale blue is the network that you could see before, and then I've highlighted one of the polymer chains in red. And what you can see is that there's lots of different points where that polymer chain meets another polymer chain. And so there's lots of points where there's a force with another polymer chain. And what we find is that when the polymer is in the solid state, if it's above a certain temperature, it actually the chains have enough energy to move and break some of those forces when you're putting stress on it, and make new forces with other chains, so they're able to move a bit even though it's in the solid state. And we call this a solid rubbery phase. So it's a bit like you might imagine rubber. It's flexible, but it's still solid, still very much solid. And if we cool a plastic down, then we get to what's known as a solid glassy state. And that, as you might imagine, is when the material becomes like glass. So if you were to hit it with a hammer, it would smash. It's not flexible at all. You can't bend it. And that's because these chains now don't have as much energy as they had when we had a bit more heat. So they're no longer able to move against each other and take up new positions as we put stress on them. And so there's another good analogy. If you think about snakes in a snake pit, snakes are cold-blooded animals, and when it's very cold, they'll all lie intertwined in the snake pit, but they won't move. And so if you were to drive a bulldozer through that snake pit, then you would either the bulldozer wouldn't be able to get through if the snakes were too strong, or it would cut right through them. Whereas if it was a sunny day, the snakes would have some energy from the sun, and they would be warm, they'd all be slithering over each other rather than still, and so if you drove that bulldozer through, they would all be able to slither out the way or slither around to let something through. So that's just another way to think about these two solid states that polymers have. And again, when we go to the liquid of a polymer, now it's melted, it has the properties of a liquid, but not a liquid like water, because again, with these long chains, we've got lots and lots of forces to overcome. And so if you were pouring a liquid polymer, it would be very, very viscous. And actually, when we're close to the melting temperature, it's often still a solid, but just a moldable one. And this is something I'm going to demonstrate in a minute. So I'll just put some of those in there. Okay. So now I am going to demonstrate some polymer properties for you. First of all, we're going to use a milk carton. Now, as you can see, this as it is, I think you would agree is fairly flexible. So are you happy that that this is in a solid rubbery state rather than a solid glassy state? Yeah? And in fact, this is polyethylene, and the glass transition temperature, the temperature at which this plastic goes from being solid and glassy to solid and rubbery, is around minus 135, I think. So we're safely in the solid rubbery phase. Now, I'm going to first of all show you a video of what happens when we put this into the solid glassy phase, when we cool it down, and then I'm going to show you what we can do when we melt it. So here I am dipping it into some liquid nitrogen. That's at minus 196 degrees Celsius. So it's cooling down, hopefully. There we are. It's moving over to the bench. Then I'm going to whack it really hard, and you can see, can't see very well. It's going back in anyway. It wasn't quite cool enough, so hopefully you'll see again on the next one. So what you should be able to see is as I hit it, then it smashes, it shatters, because it's at this glassy, it's below this glass transition temperature. There you are. Oh. Jumping back and forth here. Should have bought some liquid nitrogen here. Oh, look at that. Paused on the shot. You can see there's a small piece which has shattered off here and shattered there. And actually what I can do is show you. This is what happened. This is the actual carton. And you can see I shattered the top. And if we tried to do it with this, then it would just squeeze. There's no way it would shatter. So now let's see what we can do when we melt it. I'm going to heat this carton with this heat gun. I can't talk while it's on because it's quite noisy, so I'll explain what I'm going to do. Now the melting temperature of polyethylene is about 120 degrees. So we're just going to melt a very small corner here. And then I'm going to blow into the neck and demonstrate one of the industrial methods of processing polymers, which is where we melt the polymer, but because it's so viscous, we can then blow it into the shape we need. It's called extrusion blow molding. Okay, so let's put my safety specs on. Okay, did you see it? Did everyone get a chance to see that? Let's do it this side of it. Oh, it's just popped. Anyway. Hopefully you had a chance to see how that really blew out. And you can imagine if this whole thing was molten, then you'd get a really good effect and it would all blow into a bubble. And anyway, now I just want to just touch that for me. And what does it feel like? What sort of plastic?
Slightly sticky.
Yeah, slightly sticky. But does it remind you of any plastic material? Plastic bag, maybe? One of those food bags?
Yeah, the kind that are difficult to open.
Yeah, the kind that are really difficult to open. Yeah, and so this is a method that's used to make carrier bags. You blow giant sheets of plastic from a big blower down below, and the polymer is continuously rolled up and up. It's amazing to see. Anyway, this was just a small demo. Now, what I'd also like to show you in another demonstration is we've got some polymer beads here. Now, this is just a commercially available polymer. It's called polycaprolactone, and its melting temperature is just 60 degrees, so we can melt it really easily, and then form it with our hands, basically. So let's just. So if you look here, you can see that the polymer beads are clear, and then I can scrunch them and mold them into a ball, like that. You've got to be quick because it comes below 60 degrees quite quickly again. But you can see how, whereas that's clear, so that's definitely in the liquid state, or it was. These beads, how we receive the polymer, are transparent, so you can tell that they're in the solid state. And this is the liquid state. And even when something like this cools down, you can see we're still above the glass transition temperature, and that's minus 57 for this polymer. And because you can see we've still got that flex, oh, I've been talking too much, we've still got that flex here, which shows that we are in that solid rubbery state rather than the solid glassy state. Just get the screen back on. Now, my final demonstration, some of you, as you came in, could see we were messing around with some milk and vinegar at the front here. There may even be a little waft of vinegar that went around. But what we were doing was making a very simple polymer, which can be made from milk and vinegar. And some very early plastics were made in this way. We took some milk, which is shown there by a glass of milk, and then we added some vinegar, which was acid, and I think you probably know instinctively what happens when you do that. The milk, we call it curdling, but you form a solid lump, don't you? And actually what this is, I've got some here. Here's some that I scooped out and then have dried off. And this is a very basic form of polymer. And you can squeeze it with your hands and mold it into a shape in true Blue Peter style. Here's one I made earlier. Here's one I did last night. And it's now hardened. And again, if we think about what's happened on the molecular level, then we started with some milk, and in milk there are lots of proteins which are polymers. They're made up of chains of amino acids, but they're quite short chains. And so in the glass of milk, they're able to be suspended as the chains. And you still see the milk as a flowing liquid, but it does contain these chains. Now, when we add the vinegar, then that causes chemical bonds to be formed between some of the units on the chains. And so then you get something which is much bigger in mass than these shorter chains here. And so it's no longer able to dissolve or be suspended in the milk. And it comes out as this lump, which then hardens to this kind of resin. And this is an example of what we call a thermoset polymer. So instead of, as in the case of this caprolactone that I just showed you, or the polyethylene that I showed you with the milk, we can continually remelt, reform, recool, and melt and form and cool as many times as we want, because we're only physically changing the plastic, we're changing the state of matter. But in this case of this casein, we are actually chemically changing the material. And so you can't go back from this. We can't heat this up and come back to the glass of milk, because these chemical bonds that we've formed are permanent. And so there's some other nice examples of plastics like this. Casein itself actually was used in the early 1900s to make buttons and jewelry and ornaments. And another example is something like vulcanized rubber, where it was natural rubber and sulfur was added to cross-link it into a much less tacky and better material to use. So this is one of the classes of polymers, and the other class is the thermoplastics, which are the ones I showed you before, where you can melt and solidify as many times as you want. Okay, so that actually concludes the first bit of the talk, and now I'm just going to briefly tell you something about the research that I do. And so, although I've been talking a lot about how great plastics are, I'm now going to tell you that there are some problems with plastics as we know them. I'm sure all of you have seen some sort of photograph like this, where you've been on a train ride maybe and been past some trees that are just coated in bags. There's a lot of landfill problems with plastics. As the use of plastics has grown, so the amount of waste that we have from plastics has also grown. There's also a problem because many of the plastics that we use every day come from oil and gas reserves, which of course are finite resources, tipped to run out, but even if you want to argue that they're not going to be running out anytime soon, the price of oil is certainly not going to be going down, I don't think. And currently, it's about 7% of world oil supplies are used in plastics. So what could we do to solve this problem? One of the solutions lots of people are looking at is using biodegradable and biorenewable plastics. And so we can make a plastic from sugar beet, from corn. If we ferment the corn or the sugar beet, then we get out lactic acid. Most of you will know about lactic acid because you might have exercised too hard and got a cramp, and that's a buildup of lactic acid in your muscles. But as you know, your body deals with it very well, because if you just rest for a few moments, it goes away and you can carry on. So if we join together two of these lactide units, we form this, you don't need to worry about any of this, but you can just see it's a circular molecule. And if we open up this molecule, if we break one of those bonds here, then we can form a polymer, which has a repeat unit of this cycle, basically. And that polymer actually has a lot of the properties that polymers have that are derived from oil and gas. And it also has the added bonus of being able to be used in the body, because as I just said, if we can break it down back into this lactic acid, then your body knows how to deal with that and knows how to metabolize it. So here we are, we've got some plastics that we made. We do a reaction called hydrolysis, which just means we add water, and that water can break some of these bonds here to form the lactic acid, and then we can eventually convert all of that to carbon dioxide and water, which then theoretically we could put the carbon dioxide back into growing some plants, and that's a closed carbon cycle, for instance. So, as I've just said, there's many uses for these plastics, polylactide and related plastics. That you can use them for commodity uses, but also there are these intriguing possibilities. They're already used in these functions. Things like dissolvable stitches, bone scaffolds. If you shatter a bone badly, instead of using metal pins and supports, you can use something that will slowly degrade, allowing your bone to regrow. And there's also the possibility to use them for delivering drugs in the body. So if you wanted a slow release of a drug over weeks or months, then you could just put an implant in, and it would slowly, theoretically, it would slowly release the drug over a period of time. So it sounds, the way I'm describing it, it sounds like it's all a done deal. But of course, as with lots of these things, there are many improvements that we need to make. Now, one of those concerns the way that polylactide and these plastics degrade in the body. And there's two main problems, really. The first one is that, you remember I said we needed some water to cause the polymer to biodegrade. And, well, the problem is this polymer doesn't really like water. It's quite, we call it hydrophobic. It doesn't really let the water mix with it very well. And so in that sense, it's not ideal to need water to biodegrade it. And the other problem comes when we look at the way it might degrade in the body and release a drug. And just drawn a cartoon here. If you imagine the yellow is the polymer support and then the red is little pockets of the drug, then over time you would expect the polymer to be broken down in the body and release those little balls of the drug to then be taken by the bloodstream around the body until we have no polymer and all of the drug has been delivered. Now, if we look at a graph of how these polymers tend to behave, we've got polymer weight here and then time along the bottom. And what you can see is that often we have this very steep drop in polymer weight in a very short amount of time at the beginning. And as you can imagine, what that does is give a burst of whatever drug it is, which can then mean that you get a bit of a hit of whatever it is right at the beginning, which you might not want. And then you can see it does steady off and gives a nice degradation over the remaining time. But what we would really like is for there to be this slow, predictable degradation all the way through the profile. And so one of the ways to solve some of these problems is to take our lactide monomer, but then to add in some of these other monomers. And you can see, again, I don't need you to worry too much about the molecules themselves, but if you just see I've highlighted in red this group here, and you can see that that's what all of these have in common. And that means that they can be catalyzed and made into a polymer by the same types of catalysts because they have very similar structures. But in fact, the very small differences in structure, which you can also see, this one's got more members in its ring and then this one hasn't got these spikes, they actually create enough difference in the polymer that it allows the water. It also actually makes them more susceptible to a good degradation. If you see here, of course, when you put more than one monomer into the mix, you do have the possibility to form different sequences of polymer. So before we just had one repeat unit, and we could repeat that lots and lots of times. But if we have two choices, then we could have lots of one monomer and then lots of another monomer. So that's right at the beginning there, the block copolymer we call it. We could have a very random arrangement of the different units. So, you know, 2 of one, 3 of another, 2 of one, 1 of the other. Or we could have an alternating arrangement where we alternate between the different monomers. And what's been shown to be very good is to have this alternating arrangement, because it actually, all of the linkages you can see are blue to red. So it's blue to red, and then it's red to blue, which is the same as blue to red. And blue to red and blue to red. Whereas here we've got blue, 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 red. So here there's different kinds of linkages, because we can have blue, blue, or blue, red, or red, red. Whereas here you've only got blue, red. And so the breakdown when it happens is very, very irregular, because there's only one kind of bond to break. Now what I'm interested in is actually the design of the catalysts which we use to make these polymers. Because in the end, if we can make an alternating copolymer like this, or if we can in any way control the way our monomers are going into a polymer, then we can ultimately control the way it degrades in the end and the way it behaves, for instance, in the body or in any other use. And so I've drawn quite a crude cartoon here, but I think it makes the point. So here's a metal, and that's the real workhorse of the catalyst. It does all of the work. And then we've got this kind of red scaffold around it, and you can think of that as a support or something that really keeps the metal from doing reactions that we don't want, keeps it from joining up with other metals, and also influences the metal by putting it in a certain environment. And so we've then got atoms which join this scaffolding to the metal, and we've also got some groups hanging off the scaffold, and all of those can affect the way that the metal behaves, that the catalyst behaves. So there's lots, as you can see, there's lots and lots of areas in which we can investigate and see which are good catalysts for these processes. And just very briefly, if we look at the metals that do this job very well, this is a periodic table here, and you can see we've just got pockets of metals over here. I don't know anyone who's doing chemistry at school. We've got alkali metals here. We've got some early transition metals, and then zinc and aluminium might be familiar there. And then something down here called the lanthanide series. So there's lots of different metals to choose from, and then that's before you've even started looking at any of the scaffold or any of the other groups. So there's really a very wide variety of work that we can do in building catalysts for these processes. And just here I just want to highlight, this is a catalyst that I've worked on, and you can see how it mirrors the cartoon. In purple in the center, that's an yttrium atom, that's the metal that does the work. In grey is the kind of supporting scaffold, and then in blue and red we've got the atoms that join the scaffold, that bond the scaffold to the metal. Okay. So just at the very end, I just want to say another way we can make these alternating polymers is to actually take a monomer that has a different group at the top to what it has at the bottom. And so then, if we were to simply use just that monomer, it's like having two halves of something different. And again, you can put those into a chain in an alternating fashion so that you have different groups to attack when you're degrading that polymer. So some of you might have watched that and then kind of thought, but what about using corn for this? Because corn is a food source. And is it really an ethical idea to take a food source and use it to make a plastic when it could be feeding people? And so this is a problem, and I think in general the field is trying to move away from using food sources as feedstocks for polymers. And so here I just wanted to show you a couple of the ideas that are around, things like vegetable oil and grounds from coffee all have valuable molecules in them that can be used as feedstocks for polymers. There's also a molecule called limonene, which can be extracted from orange peel, which again is a waste product, and we can do reactions on this molecule to then make it able to be incorporated into a polymer. And actually this is also being investigated for use as a green solvent, as an alternative to some solvents. And finally, the molecule called pinene, which comes from resin, and again we can use this double bond here to put a chemical group on, which can then mean it's able to be incorporated into a polymer. So I think in terms of the future, it's certainly bright in terms of the variety of polymers we can make, and I think their uses are just growing and growing. So just to conclude, I hope you've felt over the last 40 minutes or so that you've learnt a lot about polymers. We've looked at some of their different properties. We've looked at why they're really valuable and important in our lives. And then we've also thought about how we can move forward in the future when we have reserves that are dwindling, and the necessity to kind of look for new routes to these polymers and new routes to these materials. So I'd like to just thank Alan, Dara and Ross Malcolm. They come from the Faculty of Science and Technology at Lancaster, and they're the ones who have organised this series, and they've been instrumental in its success, so thanks very much. I'd like to thank Mike for chairing the session, and he'll be taking some questions from you hopefully, and Michael Peach, who helped me make the video. I'd also like to thank members of the chemistry department at Lancaster. It's a great team we've got, and they've been a great support over the last few months. Thanks very much.